Good morning, Precalc. It is Wednesday, May 6th of 2020. Woo! Today what we're going to be talking about is how can we use vectors. So yesterday, in 10.1.2, we talked about some of the vector operations that you can do and sort of how to utilize vectors. In 10.1.1, you were introduced to the ideas of vectors in general. So what's going on today is we're going to find out why we might want to use vectors instead of some of our standard methods to solve things. And to start us off, we're going to be using an example of a plane, which is 10-31. So in it, we have a plane that flies 675 miles. I don't know why they chose m, which would be meters, from point A to point B, with a bearing of 75 degrees off of north. So they basically took their compass 75 degrees off of north. They went 675 miles. Once they got to B, they went 32 degrees off north and flew to point C, about 140 miles away. So what we're going to be doing first off is in A, we're finding the angle between B and A off of north. So we're looking at sort of this angle. Now, one of the things I sort of have done is sort of created a right triangle underneath this, which hopefully will help you out with figuring out this part. So what I would suggest doing is pausing the video here and going over both A and B and trying to figure out those angles and just sort of double checking afterwards with the video. So I would suggest pausing now. All right. So to go over this problem, what we're going to do is, first of all, with this right triangle over here, one of the things we can do is we can figure out the angle for this lower dashed line. So if I zoom in a little bit, we can figure out this angle because if we think about it, the angle underneath the 75 plus the 75 should add up to 90. So that would make that a 15-degree angle. This is a 90-degree angle, and since we have sort of the parallel lines, this would also be a 75-degree angle. And if we think about it, this 75-degree angle plus this angle will have to add up to 180 because they are complementary angles. So that means that this angle would be 105 degrees. Now, because we're looking for the angle ABC in part B, so we're looking for literally this entire angle, while we already have this 32 degrees, we have this 105, so we just add them together. So for A, the answer is 105 degrees, and then for B, our answer is going to be 32 plus 105, which is 137 degrees. Now, what we want to do is find the straight line distance for how far our plane traveled. Now, what we can do is, since we have the angle between them, we can use our law of cosines for C. And basically, we need to figure out the bearing for that direct flight afterwards. So what I would suggest doing is, if you're comfortable with the law of cosines, let me just write it down here. So for C, our law of cosines would be this length, which I'll just call C, or actually I'll call it B because B makes more sense since it's opposite of angle B. So what we're going to have is, for our things, it's going to be B squared equals A squared plus C squared plus, or minus, sorry, 2, minus 2AC cosine B. Although that should be a lowercase b, because they were talking about the angle. Or whatever, I made a mistake. But anyway, so we have side B, side A, side C, minus 2AC cosine B, which would be this angle. So if you plug it all in, you end up with B squared equals 140 squared plus 675 squared minus 2 times 140 times 675 times cosine of 137. And then as we get that, what we will do is plug it into a calculator, which when we solve it all out, we end up with B is approximately equal to 783.2. Is sort of what you get for a value of B. So that's how far the plane itself traveled overall. Now, what we need to do is figure out the angle that it went at, which is part D. So we figured out C, which was the distance. Now we need to figure out the angle. So for me, what my instincts are telling me is that to find the bearing, what we would need to do is we need to figure out the angle of A. So the angle of our triangle, angle A, which now we can do since we have the length of our B. What we can do is use our law of sines because we have B and we have the angle for B. And then we also have our, we can use that to figure out the angle A. So with this, we would have, let me give myself some more room. We would have sine of 137 over 783 equals, and then based on our thing, our length would be 140. And then we'd say sine of A. So then when we solve this out, we get 0.122 is approximately equal to sine A. And now we just have to use our inverse functions. So sine inverse of 0.122 equals A. And then we get about 7 degrees equals A. Now, what we basically can do is for our new bearing, we would have, oh, lost my pen. We would have 75 minus 7 equals 68 degrees. So we have about 68 degrees as our bearing. Now what we are going to do, so that would be our answer for D. 68 degrees. Thereabouts. Now, what we're going to do is we're going to move on to 32. Which now we're just looking at sort of a plane with a speed. So a plane that is flying at 675 miles per hour on a course with a bearing of 75 degrees is helped along by a fierce wind, 140 mile per hour, blowing towards the northeast with a bearing of 32 degrees. What is the resultant speed of the plane? Well, what we can do is, in this case, let's think of it as vectors. So we have two vectors that are sort of affecting us. So we have... So for 132, I don't know why I said 132. It's not 132, it's just 32. We have our two sort of vectors. We have one, which is like this, and this is 675. And then we have another, which is like this, and this is 140. And what we need to do is sort of find the resultant vector. So what I would suggest doing is we're going to label these vectors. I'm going to do vector P for the plane, and we'll do vector W for the wind. So let's go ahead and break these into, I'm going to break them into components form. So P would equal, if we think about it, we have our, so we're doing it vertically, so our y would be cosine, our x would be sine, or we can flip around and sort of do our angles. It doesn't really matter how our orientation is as long as we use the same orientation. So we have 75 degrees. So for the x direction, which would be this way, we're going to use sine, just based on our orientation. So 675 sine 75 degrees, comma, 675 cosine 75 degrees. And then W, our wind, we're going to do 140 sine of, what's the word? 32, comma, 140 cosine 32 degrees. And let's go ahead and get those into real numbers. So let's plug it into our calculators. So when we do this, we have, oh, 1 second. So our plane, vector P, we get sorry, 652, comma, 174.7. And so that'll be our vector P, and then for our wind vectors, so that was our plane, our wind vector, we get 74, comma, well, technically 74.2, comma, 118.7. Now, if we want to find our sort of a total velocity, what we can do is we can just add these two things together. So we'll add them together. So P plus W equals 652 plus 74. That would give us 726.2, comma, add these two together. We have a 7. Oh no, we'd have a 4. And then we add a 1, we get a 3. Another 1 ends us with 9. So we get 726.2 and 293.4. Now, we want to find the total distance, which we can just do our nice little magnitude of P plus W, which then we just invoke the Pythagorean theorem. So that would be 726.2, take the square root, plus 293.4. And then when we get that all out, we get a total of P plus W equals about 783.2, approximately. Did a bunch of rounding early on, which does make a difference. But so we get about 782 is sort of the speed of our plane, which is the magnitude of the velocity. And then what is its heading? Well, we can use our information that we have here, and we can just take the tangent of those two. So if we scroll back up and remind ourselves, we did sine here, cosine there. So we can just do tan inverse of our sine portion was over here, cosine over here. And that's just because of the orientation, since we're going off the 90 degrees rather than the horizontal, because bearings are dumb. So we do that, 726.2. Technically, if you did the things in the other way, that's totally fine. If you used cosine for x and sine for y, absolutely fine to do it that way as long as you're consistent. It's just sort of, for me, I always like to orient myself along the horizontal. If you're orienting yourself along the vertical, that's totally fine, and I will accept that. I just do not. And so over 293.4, we plug that into our handy dandy calculator. This is B. And we do that, and we get, let me just sort of plug it in real quick, of 726.2 divided by 293.4. And we get about 68 degrees. Bam. Now for C, you have the question of why was this problem not as hard as it seemed before? Well, one of the key things here is that with our things, we were able to break it up into components. So like when we're using vectors, we can break our things up into components and then add our components, and then we end up with the same sort of vectors. Oh, which I technically skipped. I thought I was... Okay. I went ahead a little bit. So like with 32, I mean, you might have been able to solve it in a different form without the component vectors, but with the component vectors, it works a little bit easier. If you look at the two questions between 31 and 32, they are actually the same question. It's just one is dealing with speed and one is dealing with sort of flying in separate directions. So the idea here is that a lot of times you have these complicated things where you have a lot of different things interacting. One of those cases is with physics and things like boats traveling down a stream with a cross current and you're paddling and all of that. What is your resultant speed? This can all be solved by utilizing vectors in a fashion that you didn't necessarily expect. And sometimes, like, the legwork is a lot simpler because in here, we converted our vectors into component form. We sort of added them together, found their distance, and took the inverse to find the bearing, while in, this first problem, we had to sort of really wrap our minds around how we're orienting things and sort of use some law of cosines to solve for the length, and then sort of do some math. And we end up solving it, and we end up, like, it takes a little bit more time. And sort of like you have to mentally wrap your head around, okay, how am I going to solve this? Whereas when you end up using component form, it just sort of breaks things down into much more manageable pieces. And that's sort of how I feel about it. Whether or not that's true for you all is another question. But for me, component form has often been the easiest way to solve a lot of these problems. So for the rest of the lesson, I'll let you all sort of solve D because I believe you can. And then with 33, which is basically how I solve 32, and I feel kind of bad about that. But if what you want to do, when you have sort of more than just two things interacting, when you have 3 or 4, component form does tend to make it a lot easier. So you're going to do 34 and 35, And that'll be what the homework assignment is. So you can basically be able to, I'm going to say you can skip 32 and 33 if you've managed to make it thus far into the video. And so really all you have to do is 10-34 and 10-35. And that is your reward for watching the video through. If you have any questions, you know where to find me. I hope you all have a great day.